See, okay. Takes more time if I record the session, okay? So if you have the handout with you, this is the beginning of, let's not pay attention to the chapter number. It's not that important, okay? But anyway, this is a new method. It's called the moment distribution method. Okay, generally, this was introduced in 1924 by Professor Hardy Cross. You know, the history says that Professor Cross was under pressure to produce the publication. So one day he came up with this moment distribution method, and it is safe to say that this method helped build the world a lot. Okay, until it was replaced by computer. Okay, now the concept of this, let's say, you know, if you can recall the slope deflection, we have three kinds of moment, right? We have moment due to joint displacement, we have moment due to joint rotation, and we have moment due to fixed moment. So somehow, if your joint doesn't rotate, the end moment of your member will be equal to fixed moment. So the concept of this is just to try to first fix the joints to calculate fixed moment, and then release the joint to unlock the structure back to its original position, and then try to balance the moment. Okay, but talk about the concept is pretty difficult to grasp. So let me try to, okay, just the wind. Show you how it works. Okay, so let's say you can have a structure that looks like this. Okay, just any joint in the universe. So let's say fixed, 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 fixed. Okay, and let me try to apply the load here. Okay, now, if I, let's call this joint with a name. Okay, let's call it A, B, C, D, and E. Now, if you look at joint E, that joint E will rotate because there's no support here. It's like the rigid joint in the air, right? So if I impose the load on this member or whatever member, joint E will rotate. Okay, so if I want to calculate the fixed end moment of every member, let's say member EC, because it's the only member with the load, okay, I will lock joint E. Okay, so step number one is to fix the joint. To calculate fixed end moment. Okay, so if joint E is fixed, generally this load will create moment in this direction, correct? But we are in slope deflection, we are always interested in resisting moment. Okay, so yes, we will see that if this is the direction of the moment that this load produces, your resisting moment will be in the opposite direction naturally. So that becomes your resisting moment, okay? Resisting moment. Okay, so once this is complete, if you lock the joint, you can easily calculate moment, right? You can easily calculate your fixed end moment. But because that is not the natural condition of your structure, if you lock the joint to calculate moment, you need to release it back to its original position. So in step number 2, let's say if I'm trying to be more colorful so that it will be, I hope it helps. Okay, at the same color. Okay, I am going to release the joint back to its original position, so to speak. So when I release the joint, you know, this joint E, okay, will rotate due to the load, right? So this moment from the actual load will continue to rotate the joint. But we have the resisting moment coming from each member. You see, the green one is in the same direction as this. So it will try to resist this. Okay. Okay, let's say this is your step number 3. After you release the joint, oops, that's the wrong color, right? Moment will be balanced at the joint. That's not, doesn't look like a good J, so let me fix that. Okay. Let's say, give it some name, okay? This comes from member EC, so I'm just gonna call it MEC. And that is MEB. This is MEA, and this is oops, sorry. This is MED, okay? Now, after this occurs, you know, if I focus step number 4 now. If I look at the joint, these joints are formed by members, right? So in the end, I have this member, that member, and then that member, okay? So if you have this green one, you know, it has to be balanced. So that will be moment equal and opposite to the green moment, you know, at the member, correct? So that if you focus on the connection between the joint and the member, it is under equilibrium. All right. So that with this moment, and then this moment on the member. So when you focus on the member itself, you know, like this, the fact that there is a presence of the member of the moment on this member means that somehow we need to also find the equilibrium for the member. In other words, that means the presence of this moment must have the effect on the other end, or in moment distribution we say that this moment must be carried over to the opposite end of the member. Moment will be carried over to the opposite end or the far end. Okay, so this is the basic concept of the moment distribution. Think about, even though not many people use it nowadays because of the computer, but I am always amazed by how, an engineer, the Professor Hardy Cross, could come up with the concept to create the mathematical solution out of the lock and release process. We could do this without ever having to solve any equation. Okay, and you fix the joint, to calculate fixed end moment and then release it. And upon releasing it, you know that all the members at the joint will help balance this moment. So the first question is, how much each member will help contribute in balancing this moment? Okay. How much each member helps? Okay, because when you release the joint, the moment will come alive again and it needs to be balanced. So one question is, how much each member will help contribute in balancing this unbalanced moment? And another question is, when this moment occurs to help balance, it must be on, the member as well. And this moment will be sort of carried over to the opposite end. So the next question is, how much moment is carried over? So we have two questions to answer. Okay, and let's say this is question number 1. This is question number 2. The answer to the question number 1 is something we call distribution factor. Or in short, DF. The second is something we call the carry over factor. Okay, and it's easier to start with number 2. So I think that's what I would do. I would start at number 2. There is explanation available in the handout, but I think I prefer to do everything from the beginning so that you can see it. If you just look at the PowerPoint or the handout right away, it doesn't have the origin or it doesn't show you how things are developed. Okay, so let's say this is your condition. Okay, let's say one end is fixed and one end is going to rotate. So it's safe for me to write it like this. Okay, and let's say you rotate like that. And if I may call this joint I call this joint J, we will have the let's use the different color rotation, and your member is going to deform like that, and this comes to 0. Okay, so let's say we are focusing on the carryover factor from I to J. So J will be fixed this time. And so you have zeta I and you have MIJ. okay? And I can write down Mij by using my slope deflection equation. So it's going to be 2EI over L 2 zeta I plus zeta j minus 3 psi plus fixed end moment ij. But like I say, we focus only on the Mij and the fact that the joint I rotates. So for now, I can say zeta j 0 because I focus on joint I. And the psi term is also 0. And we don't have fixed end moment. So I can write down Mij as 4EI over L. And Mji now, 2EI over L, 2 zeta j plus zeta I minus 3 psi plus FEMJI. And again, zeta j is 0, psi is 0, and fixed end moment is 0. So Mji is 2E, oops, I forgot zeta I here, sorry. 2EI over L zeta I. So you can see that Mij is 4EI over L multiplied by zeta I. In the meantime, Mji is 2EI over L multiplied by zeta I. So I can safely say that Mji is equal to half of Mij. Can you see that? You compare these two values and you see that Mji is only a half of Mij, which means that whatever Mij you have, let's say your system has Mij, it will cause Mji to occur 50% of Mij always. So from this, we can say that whenever there's a presence of Mij, there will be 50% of Mij on this side. So it's safe to say that 50% of Mij will be carried over to the far end or to the opposite end. So we can say that our carry over factor is always a half. That beautiful, right? Okay, next is the distribution factor. Let me go to the next page so that let's hope that I can keep everything in one page. Okay, so let's come back to this. Yes?
Can you go back, please?
Okay, sure. Thanks for, participating. I really do appreciate hearing from someone, even though it's just a request to just go back.
Thank you, teacher.
Cheers. Okay. Oops. Now it wouldn't go. Okay. Here we go. So let's go back to the system. Let's say this is what we have. Okay. And we are going to have this kind of rotation, right? Because we sort of apply the load here. Okay, so that becomes a deflected shape. But one thing that we do know from this is that this is still our rigid joint, right? So I can say that the rotation at the end of each member should be equal and have the same direction. So I can say that you can recall that this is joint E, right? And honestly, I don't remember where I have the A. So I think so that's the A, B, C, and D. So when I put my interest on my moment slope deflection equation, I should know that zeta EA should be equal to zeta EB, should be equal to zeta EC and zeta ED respectively. Okay. And you know, from my moment equation from the previous page, remember I have this equation, you know, so from Mij is equal to 4EI over L zeta ij, you know, I can rearrange this term a little bit so that I can write my zeta ij in terms of moment, and that would be equal to Mij multiplied by L over 4EI. And likewise, I can substitute ij with EA and EB and so on and so forth, right? So that means I can easily write this equation again in terms of this. So I can have MEA, okay? And let's put things in perspective. I'm gonna try to put the L down here so that you can see better. So it becomes 4EI over L. This has to be equal to MEB 4EI over L. But okay, yeah. EI over L, I over L should be of that respective member. So maybe it's wise to have the subscript EA, EB. This shall be equal to MEC. You know, they have blocks and I don't know why I don't use them, but sorry. 4EI over L of member EC and of member ED, 4EI over L of ED. Okay, so this is from this equation by, you know, substituting the value of zeta. So we have that. Okay, now we know that in the end, you know, the equilibrium must prevail. So I can say that sigma ME must be equal to 0. That must be true. And that means I can write down MEA plus MEB plus MEC plus plus MED plus sigma fixed end moment, whatever you have, the total fixed end moment at joint E. So I can write this now. Total fixed end moment at the joint. And you guys should believe in superposition, right? I got more than one question, you know, from you guys saying, can I use this formula and that formula to combine, to calculate fixed end moment? I believe I have shown you guys in the class how I can calculate reactions from each load and then combine in the end, right? If I can do that with the reaction, I should be able to do that with the moment as well. So anyway, this better be 0. Okay? But, you know, let's say I will go back to this. Okay? And if 4EI over L is called K, you guys should begin to realize that this is the stiffness of your member under bending. This stiffness relates moment to rotation, and it becomes the value of the stiffness of any typical member. Okay, if you call that stiffness K, I can rearrange this equation and write them down like MEA over KEA is equal to MEB over KEB. It's equal to MEC over KEC. Let me try to fix this, and just doesn't seem to be very readable at all. MEB over KEB and equal to the last one MED over KED. Okay, but you can see if you have something like this, it means that I can write my MEB in terms of MEA, right? By using this relationship. I can write my MEC in terms of MEA using this relationship, because they're all equal, right? And the last one, I can also write my MED in terms of MEA using this relationship. Okay? And you know, it's gonna look like this. So for let's begin with the green one. I can say that MEB is equal to KEB over KEA multiplied by MEA, right? And in the similar fashion, MEC can be written in terms of KEC over KEA MEA, and the purple one as well. So I don't think I need to write them. Okay. So when I replace this and put this back in this equation, I can now have MEA plus MEB becomes KEB over KEA MEA plus, you know, I try my very best to make it, you know, readable. Let me try again. Maybe I should reduce the size. EA MEA, okay, but it doesn't look very clear. So for those with the problem, I'll change that K E C over K EA multiplied by MEA again plus KED over KEA and then MEA and then plus the friction moment, okay? Just running out of space. So with that, and I try to keep it, you know, with the same kind of format. So I will put KEA over KEA up front. Okay, and this plus let's say do it here plus sigma of fixed end moment at E will become 0. Okay, so now you can see that we have all the denominators here. The denominator is always KEA. Okay, and therefore I can rearrange this term a little bit, but I am out of space, so it's to the next page. I can now write this as let's say, you know, try to put things easier for you. So I have K, oops, sorry. I have K EA plus KEB plus KEC plus KED. This is divided by, oops, oh man. This is divided by KEA, and then we have MEA. I move the fixed end moment to the opposite side, so it becomes sigma FEM at joint E. So you can see the pattern is forming now, right? I can say that this is the summation of the stiffness at joint E, right? Because it consists of every member stiffness. So you can see now that my MEA is in fact equal to KEA divided by sigma KE multiplied by sigma FEM at joint E. So, ladies and gentlemen, this is the distribution factor of member EA. Or we can just call it DF. Okay, it will tell you how much each member will contribute in balancing the moment. Okay, so we have determined, we have identified the carryover factor, which is always 1.5. And we now have also identified the distribution factor, which is the stiffness of that particular member divided by the summation of every stiffness of every member that help form the joint. So that's it for the concept of the moment distribution. So before we take a break, let's look at this a little bit. So, you know, it's in here. carryover factor is always a half, and this is blank, but you have that in there. So after the concept, you know, we can say the practical procedure of moment distribution can be summarized as follows. Okay, first you define the relative stiffness. You need the K to calculate the distribution factor. So again, I can write down here that you need, okay. You need K for your distribution factor. So again, if you get your stiffness wrong, your distribution factor will be wrong, and you will be, you know, dead at that point. Okay, so after you have the K, which is the relative stiffness, you can obtain your distribution factor here, calculate friction moment, and determine the unbalanced moment, or just simply the summation of friction moment at the joint, you know, and then calculate the resisting moment by using distribution factor, then carry it over 50%, and then we will repeat this step as necessary. Okay, so then that's it for the moment distribution. Okay, is there any question with the concept? You know what, let me stop the share and stop the record.